Hello everyone. Today we will be continuing with our discussion on random variable and Borel functions. So we have defined a Borel function. Let me revise that. So we defined Borel function as some function g from Rb to Rb. This doesn't have to be Rb. We can actually have a subset of R and corresponding Borel sets also, such that for every S in B, G inverse of S should also be in B. Okay. Inverse image of every Borel set should also be a Borel set. That is our definition of Borel function. Okay. So today we will prove that Borel function of a random variable is also a random variable. Okay. We prove that Borel function of a random variable is also a random variable. So suppose x is a random variable from omega script a to Rb, and now y is some function of x. Okay, and this g is a Borel function. Now remember, even though right now I am writing it as g of x, it is actually g of x of omega, right? So I can write this y as a function of omega, where y is actually g of x. Okay, so if I want to take inverse image of a Borel set with respect to y, then it would also be consisting of omegas, and hence it would also be subset of this capital Omega. Okay, so that is what actually we have to prove now. So to prove that y is a random variable, what I'll need to establish is y inverse of s is in script A for every s in script B. Okay, that is what we will need to establish, that for every Borel set, inverse image under y is in script A. So let us consider. So y inverse s would be, by definition, set of all those omegas in omega such that y omega is in s. I am just writing down the definition, nothing else. So this is set of all omegas such that g of x of omega is in s. Okay. So this is same as set of all omega in omega such that x of omega is in g inverse of s, because gx of omega is in s is same as saying that x of omega is in g inverse s, and we know that g is a Borel function, therefore g inverse s is also a Borel set. So this is some other Borel set, and now this entire set becomes, by definition it is set of all omega such that x of omega is in g inverse s. So this is same as saying that this is inverse image of g inverse s under x, right? Set of all omega such that x of omega is in some set. So it becomes inverse image of that set under x. And since this is the Borel set, and since x is a random variable, x inverse of any Borel set is in A. So this is in script A, and that is what we wanted to prove. So we have proved that y inverse of s is in script A for every Borel set s. Therefore y is a random variable. Okay. So what does it mean? It means that every Borel set, every Borel function of a random variable is a random variable, and every continuous function is a Borel function. There can be some non-continuous Borel functions also, but every continuous function is a Borel function. So we can say that every continuous function of a random variable is a random variable. That's why e raised to x is a random variable, log x is a random variable, sin x is a random variable, x square is a random variable if x is a random variable. Okay, so all these become random variable if x is a random variable. Okay, now we have one more small result. What can we say about y inverse of s? So we just now proved that y inverse of s belongs to A for every s in script B. Okay, therefore y inverse of A is actually subset of A. That is okay, but we can actually prove that y inverse of script B is subset of x inverse of script B. How? The same steps over here. See, we showed that y inverse of S can be expressed as x inverse of some other Borel set. Okay? Therefore, if we take any Borel set and take its inverse image under y, it is same as inverse image of some other Borel set under x. Okay? Therefore, from this step, I can say that y inverse of S belongs to x inverse of B for every s in B. Okay, inverse image under y of every Borel set is in x inverse B, and therefore y inverse B is subset of x inverse B. Okay, so let me emphasize what I am trying to say. If this is x inverse script B, so this is collection of inverse images of Borel sets under X, then inverse images of Borel sets under Y is a sub collection. Okay, so this becomes y inverse of script B. Okay. Of course, in some cases they can be equal to, especially when you have say 1 1 onto function. So if y is 1 1 onto function, then it would mean that x is also a 1 1 onto function of y, because they are kind of you can define kind of an inverse function. In that case, your x inverse of script B would be same as y inverse of script B. Okay. For example, e raised to x, it's a 1 1 function. So if you write y equal to ex, you can also write x is equal to log y. So both are functions of each other. So in such cases, x inverse of script B would be same as y inverse of script B, because both can be written as functions of each other. So by this logic, x inverse of script B is subset of y inverse script B, and reverse way is also true. Hence finally they are equal. Okay. So these were some points about Borel functions of a random variable. Now we have to go one step ahead and we have to define what is meant by a random vector. Okay. So because you have studied multivariate analysis, or you will be studying multivariate analysis, so we need a concept of random vector. So let x be defined from omega script A to rk bk. Now two questions. What is rk? What is bk? So rk is r cross r k times, and bk is k dimensional Borel sigma field. What do I mean by that? What I mean is, just like one dimensional Borel sigma field is constructed from intervals, we can construct k dimensional Borel sigma field from rectangles. Rectangles are equivalents of intervals in higher dimension. So for example, if I am in 2D, then I can have say a1 b1 here and a2 b2 here, and collection of xi's between them becomes a rectangle. Okay. So let me define, say, for a particular rectangle as collection of all x such that ai is less than xi is less than bi for every I in 1 to k. This is a particular rectangle. This can be written as a1 b1 cross a2 b2 up to ak bk. And if C is collection of all rectangles of this type, okay, C is collection of all R's, or you can write C as, say, a1 b1 cross a2 b2 cross ak bk such that ai's are in R, bi's are in R, and ai's are less than bi's. Then sigma field generated by this collection, minimal sigma field generated by this collection, we denote it by Ck, is nothing but Bk. Okay, Borel sigma field in k dimensions. And a random vector is defined with respect to this. So how do I define a random vector? Let x be defined from omega script a to rkbk. We say that x is a random vector, or if x is a Borel measurable function, if for every s in bk, now you are taking k dimensional Borel set, x inverse of s is in script a. Okay, we are taking k dimensional set, that is important. So let us take some example. So let me take omega as, say, a, b, c. Okay, let us take some real example. So we are suppose having omega as, say, throw of a die. So 1, 2, 3, 4, 5, 6. Okay, and I define x of omega as, say, omega itself, identity function, and let me call it x1, and x2 of omega as, say, omega square. So omega square means x2 of omega is 1, 4, 9, 16, 25 and 36. And we define a vector x1 omega comma x2 omega. So what are possible values? 1, 1, then 2, 4, 3, 9, then 4, 16, 5, 25 and 6, 36. So this is if omega equal to 1, 2, 3, 4, 5, 6. Okay. These are possible values of this random vector. So if I try to construct inverse set under this vector x, depending on these, I am going to get something, right? So for example, we have too many, but if I take something small, maybe I can actually write down. So let me take some smaller example. So suppose omega consists of a, b, c. X of omega is equal to 1 if omega is either a or b, and x of omega is 2 if omega is c. Let me call this x1, and x2 of omega is suppose 2 if omega is a, c, and 1 if omega is b. Now what are possible values of vector x? When omega is a, it is going to be 1, 2. When omega is b, it is going to be 1, 1. And when omega is c, it is going to be 2, 2. Okay, how am I doing this? Omega equal to A, then x1 is 1 and x2 is 2. So I get 1, 2. When omega is B, x1 is 1 and x2 is 1. So I get 1, 1. Okay. Now, inverse image of any two-dimensional Borel set, we can call it S2, would depend on whether it contains any of these. So if it contains, so it can be singleton A if it contains 1, 2, but it doesn't contain the other things. So this doesn't belong to S2 and 2, 2 also doesn't belong to S2. Similarly, inverse image under S2 will be B if 1, 1 belongs to S2 but other two don't. So you can list all the elements, that is your homework, list all possible elements, and you can actually try and prove something. So you can actually try and prove that sigma of x inverse of B union x inverse of x1 inverse B, x2 inverse B is actually same as vector x inverse of B2. Okay. So we know this is the sigma field with respect to which x1 is measurable. This is sigma field with respect to which x2 is measurable. We also know that union of two sigma fields need not be a sigma field. Hence, we have to take sigma of that so that it becomes a sigma field, and it can be proved that it is same as x inverse B2. I want you to work this out as an example. Okay, so in this particular example, I want you to compute. There is another important result, that is x is a random vector with respect to omega script A if and only if x1 and x2 are random variables with respect to the same sigma field. Okay, so basically it's an equivalent definition of random vector. You can say something is a random vector if and only if every component is a random variable. Okay, so what does it mean? We will use this result. So let us assume that x is a random vector and try to prove that every x is a random variable. So x is a random vector would imply that sigma of x, let me write one step more. It means that x inverse B2 is subset of script A, but we also know x inverse of B2 is sigma of x inverse of B union x2 inverse B. So this is subset of A. If sigma field of something is subset of A, then we know that the components, so x inverse of B union x2 inverse B is also subset of A. And of course, it also means that individually x1 inverse B is subset of A and x2 inverse B is subset of A. Okay, so x1 and x2 are random variables because that's what we need to claim that they are random variables. Conversely, if x1 and x2 are random variables, then this is true, this is true. Hence, this is also true, that is x1 inverse B union x2 inverse B is also subset of A. And now, since script A is a sigma field, by definition of minimal sigma field, I can say that sigma of x1 inverse union x2 inverse B would be subset of A, and that is what we want. Okay, thus we have proved that x is a random vector with respect to script A if and only if x1, x2 are random variables with respect to script A. Okay, so these are some of the important properties of random vectors and random variables. We'll stop here for today. We'll continue in the next lecture.